What happened? Ah, yes. My screen should be visible now.
Yes, sir, it is.
Yes, sir.
Okay. Okay, so today we will see a very short introduction to what we call abstract data types, often abbreviated as ADT. Essentially, this consists of two things. So what is an ADT? It's a thing, first of all. Such that it is specified one, what the thing consists of, that is its components, and what we want to do with the thing, with it. Okay. The thing may be a collection, maybe a set, something like that. And we precisely mention what that thing consists of, that is, what are the components of that thing, and second, what we want to do with it. As such, when we talk about abstract data types, we do not attach to this specification a thing, this thing. Okay, so I will say an ADT is a data structure if it is additionally specified how the components are organized in memory, let's say. Okay, so an ADT, so a data structure is an ADT plus some kind of implementation details or storage details or organization details. Okay, so in this course, we will not look at serious data structures, but today I will talk about two ADTs, which are very simple but fairly useful. Stacks and queues. I will tell what they consist of and what do we want to do with it. Okay. So first, let us look at a stack. Let us call it S. This is basically an ordered list with a specific n called the top. Okay. Ordered list means, of course, it's a finite ordered list. Ordered list means there is a first element, there is a second element, there is a third element, okay, and so on. So the list is finite, so it starts somewhere and ends somewhere. And one of these two ends we call as the top. The other is called bottom, but it's not so important. And the operations that we want to do are this. So that means the operations that we want to do. Maybe for the time being, let us say a stack of integers. It may be many other things, stack of characters, stack of student record, stack of files, and so on. Initialize means S becomes an empty list containing no item. Then you may ask for this. This returns the top of the element, top of the stack. Top means the element at the top of the stack. And there are two other important things. One is called S, push S X, and pop. So push means at the top end of that stack, push the new integer x, and pop means just delete one element from the top end of the stack. So these are the four things. There are other things might be like.
So why do we call them abstract data types? Like normal, why don't we call them normal data types?
Yeah, abstract in the sense when I specify this, it's an ordered list with a specific end called top, and this. I am providing no hint on how to implement a stack. It's just
Okay,
an
sir.
abstract definition. This is the thing, and I want this to be this. I mean, these four operations: init, top, push, and pop on stack. This is an abstract definition. Okay, without any
Yes, sir.
implementation. Okay. Now, of course, when we have an ADT, we should have some implementation of it. So there are two possibilities. There are many other possibilities. One possibility is an array implementation. Now this becomes no longer abstract. I am looking at the implementation. So if I have an array like this, if I draw it like this, it is a natural thing to call this the bottom. We will never access the bottom, but this is the top. Okay. Push means I simply push the new element. Whatever earlier was there, they will stay, and the top will go here. Okay. And pop means, so this is the result of push. And if I make a pop, it once again becomes this. So I had something like A, B, C, D here. Same thing. Okay. And if I pop, I simply take out the top element and let the top move down. So for a natural, for an array, this is a natural implementation. And this actually shows, this actually looks like a stack. Let's say a stack of plates. So maybe these are A, B, C, D are plates. So when you want to add a plate, you typically add it at the top here. Usually what you do not do, you take out A and B and then insert that thing and then again put back A and B. Okay. So that kind of operation is not what we want to do in connection with stacks. Similarly, if I want to take one plate it is a natural thing to take the top one. Okay. And that is what it happens in marriage functions and other functions. You take this plate. And when you are done, there is a pile of plates, something like this. You simply put your used plate on the top of that pile. Okay. Okay, so that is about an array implementation. Fairly straightforward, right? I will do actually some kind of implementation, not array and not stack, so that it gives you some more practice on, I would say, linked list programming. Okay, I will do that, but before that, I can also have a linked list representation of a stack. So I have something like this. A linked list is naturally an ordered list, right? This is the first element, this is the second element, this is the third element, this is the fourth element, and I have a header. I have a header. And some data, 15, 9, 64, 37. Okay. Now, if we have a linked list implementation, there are two ends. This end I can use as top. This end also I can use as top. Which one is more natural, do you think?
Sir, at the end where there is a null point like the 37 one, that
So
node.
this is by your suggestion. This should be the top.
Yes, sir, because we can extend from it directly if we need to add nodes.
Okay, so now let us see how a push operation goes. Of course, in addition to this header, you can actually maintain a top pointer here. That's not a difficult thing. You say this is my top, and I am storing this top as a pointer, and also in order to store this list, I need a header. So if I want to push a new element, let's say 75, I will allocate something. I will change the link here. This will be my null pointer. I will simply change this top from this to this. Right.
Yeah, but this is like the header, the start, like the point where we add and remove points, then we don't have to use two different pointers for variables.
Actually, just one pointer is not a critical issue, but there is still a critical issue here, as you will see. Now, suppose I want to pop. Then this 75 will go.
Okay, we don't have the previous.
Yes, so we will have to maintain the previous pointer as well.
Yeah, so I have to somehow readjust this top to move from this location to this location. And without extra support, how can you do that? The only way you can do that is just traverse this entire list until you find the node whose link is null, right? So if there are n elements sitting in the top, in the stack, then you essentially run a loop which runs or which executes for n iterations. Therefore, push with this representation is fine. Pop is inefficient. Right. Therefore, the better approach is I use the beginning as the top. This is not a problem. In fact, In fact, you can draw the list this way. And this is my top point. Okay, so if I draw it this way, 8, 95, there is no problem, right? Now what happens if I want to insert a new thing? I will malloc, that link will go to the old top, and the top will be this. And if I want to pop, I'll simply free this node if freeing is needed. Before that, I will hold this pointer somewhere, and then I will simply change top to this. So with this convention, both push and pop are efficient. So there are two ends. Any end I can use as top. No problem, right? If I make the beginning of the list as the top, then both push and pop are efficient. And therefore, this is the preferred way. Okay.
Yes, sir. Understood.
Okay. So the stack is a simple data structure, and I leave the implementation of a stack, these functions to be more precise, init, top, push, and pop to you. Let us go to our second data abstract data type. Queue. So it's like a bank counter, cashier sits here, and you have a queue of people waiting. Okay, and this is the cashier, money, all that stuff. Okay, so this is once again an ordered list because the person standing closest to the cashier, he will be served first, then this guy, then this guy. And if a new person comes, should join not here, here. So that means there are two ends of this queue. This end is for deletion, whereas this end is for insertion. Okay, so a queue is basically once again an ordered list. Okay, so this is deletion end, this is insertion end. So queue is once again an ordered list. One end is called front or head, and that happens to be the deletion end. The other end is called back or rear, and this happens to be that end where insertion takes place. Okay, so it's again an ordered list with two ends. One end is called front, the other end is called back. So this is the I would say definition of whatever the components are. Then I have to specify the operations that we would like to do on a stack. Again, on a queue. Init, create an initially empty queue. Okay. then you can actually, you are going to serve the element sitting at the front. So front Q, this is to return the element at the front of Q, provided that Q is not empty. If it is empty, this should return an error message or something like that. Okay. Then I have insertion and deletion. So insertion and deletion are general terms. In the context of queues, insertion is called an NQ operation. This is similar to push, but when we talk about queues, we do not call push, we call NQ. And a deletion, which is again a general term, in the context of queues, it is called DQ. Okay. So here X is inserted at the back. And here the front element is deleted. Okay. So these are the 4 operations. There are other things like if you go for a stack implementation, we may check whether it is empty, whether it is full, and several other things. But this is the basic operations: initialize, check the front element, then NQ and DQ. Okay. So now we look at some implementations of this. So using arrays. Think of this array like this, and maybe your queue sitting somewhere here. The array may extend up to this point. Okay. So again, I have 2 ends. This is 0. Let's say max size -1, and the current size, if that is n, this is n -1. Which one should be front and which one should be back?
So front should be n-1 and back should be 0.
Of course, these are 2 possibilities. This is front, this is back, or this is back, this is front. So suggestion came that this should be back. This should be front, this is back. Okay. Now, of course, if I want to delete, that is DQ, I simply decrement this front pointer. How do I insert?
So there will be a problem in insert.
So we
We have to put all the elements.
Yeah, we have to shift all the elements. Okay. So shift all during NQ. So there is other option. Let us call this front. Let us call this back. Then how do I NQ? Simply add a new element here.
We just add it in the next index.
B becomes B++. Right. Just make B++. Front. What about dequeuing?
So remove the first element and then like if you want to save space, then shift all.
Shift in the forward direction by 1 space. So we remove the the element at index 0 and then shift all the elements by 1 index.
Yeah.
Towards
so
the
this
front.
happens in a natural queue, right? When these guys serve, everybody comes forward. Okay. Actually, everybody does it happily because he or she is just one step forward. But in the case of computers, this is actually a problem, right? If we follow this convention, then again shift all the remaining elements during DQ. Okay, the computer has to do it. Okay. Happily, these elements will not just move forward by one step. It will not happen. Okay. So whether we make this convention or this convention, either NQ or DQ becomes inefficient. If we, for example, have a very long queue of 1 million elements, then we have to make 1 million shifts with this convention for NQing, with this convention for DQing. Okay. So,
if this array is, if the array is not static, then can we not add one means 4 bytes of means whatever it may be in the back and join
yeah,
it?
I'm coming to that. So either this is inefficient or this is inefficient. So what I will do, I will create a trick, apply a trick. Say initially I have my front here, my back here. Okay, so this entire part is my current queue. Then I have a DQ. What I will do, I will not relocate the element, all these things here. But what I will say, I will allow start here, the queue to start here, front here, back here. Okay. Then once again maybe some NQ, NQ, NQ. Once again, if I make a DQ, what will happen? I will skip 2 elements, and from here to here, I have my queue. This apparently looks fine, but you see that eventually the array will run out of space. If the array is of size S, then after S DQ operations, there is no position left in the array to store the queue or anything for that matter. Yes or no?
Yes, sir.
Yes.
Okay.
Yes.
Somehow we have to handle this problem. And the problem can be, okay, handled in this manner. Use this array in a circular fashion. Which means that we will do similar thing, and let's say for the moment I have something like this. This is my front, this is my back. Then if I want to NQ, I will not go here. I will see whether there is some empty space in the beginning. If so, I will NQ this new element here, and I will say this back pointer is here. Okay, so as if this side is fused with this side, then I can always have a continuous, this is the same as this side, so after this thing happens. So at some point of time, maybe my queue starts here, ends here. Okay, and the index arithmetic should be computed modulo the size of that array, which is S. Happy or not? Then I can effectively use the entire array, right? There is a very small catch here. This is interesting, so I just mentioned. Suppose I have a situation like this. I have a single element queue. So this is both front, this is both back. So one element queue. So after I make a DQ, what should I do?
Sir, I should move the front back to the array index 0. The front pointer, I mean.
I want to be uniform with respect to the other things. I move front. Okay, what happens if I have a DQ operation here? I simply f plus plus, but this plus plus is modulo the size of this array. Here also the back is unaffected. Okay, here also if I just want to DQ, I will increment f modulo s, of course. Back will remain unchanged. So if I do this same thing here, I am assuming that I am not externally maintaining the size.
So then both have to be changed, front and back. So in this case, if we DQ, we will have to change the position of back and front both, because then the front will move ahead if we do f plus plus.
How do I know? How do I know? I am not maintaining the size of the key. I am only maintaining this front pointer and back pointer, nothing else. Do you understand?
Yes, sir. Yes, sir.
Okay, so that is the specification. I have an ordered list starting at F, ending at B. That's what I would like to store, nothing more. Okay. So DQ means F plus plus. Okay. Back pointer I am not touching. Okay. So this is basically an empty queue. Okay. On the other hand, if I look at a situation where the queue is full to the capacity, if it starts here, if this is the front, goes here, comes back here, and B. Okay, so now I have this going here and then coming back to this. So this is my configuration for full queue. Happy or not? Yes or no?
Yes, sir.
And this is the same as this. So empty queue and full queue, they are basically the same. Did not? F is just one more than B modulo the size of the array. Do you agree?
Yes, sir.
Okay, right?
Same. Yes, sir.
So this is a problem. This is a subtle problem that we need to solve. There are two solutions, maybe many other solutions. First solution is this. Maintain queue size externally. And when the size is 0, although this f is equal to b plus 1 modulo s, if you maintain the size, if it is 0, it means empty queue. If it is s, the allocation size of the array, then it is full queue. Another another solution is this: don't allow the array to be completely full. So the second solution essentially means that, true, I will start from here, and if space is needed, I can jump to this point but I will not allow it to be filled to capacity. I will keep one element okay, and if that convention I follow, of course I am wasting this extra space for one array cell, but then the condition for empty queue is f equal to b plus 1 modulo s, whereas the condition for full queue is f is equal to b plus 2 modulo s. Okay, but this comes at the cost of this extra space for this extra cell, unutilized cell, right? And in this solution, of course, I have to maintain this external size of the queue externally, so that also implies some space. Okay, but anyway, these are two ways by which we can have a decent array-based implementation of the QADT. What I will now do, maybe I have just 15-20 minutes, is just sufficient perhaps to go for a linked list based implementation of queues. And this is what I will write code of. But before doing that, let us fix our conventions prudently. Again, I have two ends here. This may be my front, this may be my back, or this may be my back, this may be my front. Which one is better?
Sir,
So we will keep the header as the front and the
So front
last node as the back.
So this is your
yes,
side.
sir.
sir,
Okay.
Yes, sir.
well, I think it will not matter because we have to access both at the end of the day.
Think of this.
I think the header should be the back.
Yeah, don't think. Think of this thing that just argue this way. At the front position, we will only insert. Sorry, we will only delete.
DQ.
Whereas in
We
back
will
position, we will only insert. Insert is easy here, given this pointer. Insert is also easy
Sir.
here, given this pointer. Deletion involves something of concern. If I delete here, then in order to keep this pointer, keep track of the previous node, I once again will have to traverse the entire list and find the last node. Happy? Because
Yes,
we do not have reverse links. Okay. On the other hand, if I make delete here, this becomes this next. Okay. So this is the important thing. Insertion or enqueuing easy at both ends. Easy means efficient. Deletion, efficient at beginning and not efficient at end, because I have to find out the previous point. So that essentially limits my choices. Since deletion is efficient at the beginning, so I will make this front, and insertion is easy at both ends. So if this forces me to be the front end, and this will have to be the back end. So I will have insertion here, sorry, I will have deletion here. Yeah, deletion is front, and I will have insertion here. Okay, so insertion is basically enqueuing. This is basically dequeuing. Okay. So with this convention in mind, I will now implement these operations because this will just give you a practice of some kind of linked list programming. First of all, I have to define some structure for a node. Data, element, or whatever you write, key. Then I have struct underscore node star next pointer or pointer link, whatever you call. And let's say I am calling this a node. Then I will define a data type for Q. What will it consist of? Tell.
So the header and the
Front and the back pointers.
Yeah, I want only these 2 pointers. Nothing else I want, right?
Front and back pointers.
So it will be node star F, node star B. Okay, that's all I need. The entire list otherwise will be linked using this next pointer. I do not need any specific, I would say, storage for storing this list here. Just 2 pointers will suffice. Then how will my init work? So init means I am creating an empty queue, and therefore front and back both pointers should be null. Okay, so if I return like this is another construct you learned today. Will it compile? Let us try. So this is null, this is null. Should it compile? What is your suggestion?
No, sir.
It will not compile. Let us see. Error. Expected expression this. Expected expression before this token. How can I get rid of this error? Can I, first of all?
But sir, how can we return 2 types of return, means 2 data types in one return?
What is it? What did you say?
So can we return 2 data types? Means
We can return any structure. Any structure.
sir, change the return type to Q star maybe.
Star, of course, we can do. Anyway, let us see. typecast it to Q type. Let us see what happens. Okay. So this is a trick you just learned today. You can use this. Because in C you see comma within curly brackets, something comma something comma something. This may be an array. Okay, this is how you initialized an array, right? We also use the same notation for initializing structures, right? Now when I use
Yes,
this,
sir.
compiler doesn't know what kind of thing it is. If I explicitly say it is a Q data type, then it will simply typecast and return this thing. Okay, happy? Okay,
Yes,
good.
sir.
It will return a array.
No, it will return this thing, 2 pointers clubbed together. Okay.
Okay.
So whatever this thing,
Basically, we are putting values in Q.
yeah, it may be just
Returning
16 bytes. All these 16 bytes will be returned. Okay. So here I have Q. I will just say Q equal to init. Okay. Maybe it gives some error message. I have variable set but not used, but that's a different thing. I will use it later. Okay. Then I have front. I will write it.
NQ function.
NQ function maybe I write. NQ X. Okay, so NQ was where? NQ is
At the back.
Back. Okay. So one thing I need to check. Of course, first I need a pointer. P equal to node star malloc size of node data. P data will be X. P next will be null if Q dot front null. So that essentially means Q dot back should also be null, but anyway. Then return the single element list. I can once again use this Q P comma P. Happy? If Q dot front is null, then back should also be null. We will make sure that not one.
Sir.
Huh?
Sir?
Uh-huh.
Okay, no. Okay, understood.
Okay. Otherwise, I have to make a real insertion at the end. What should I do? Insertion is at the end, right? So Q dot, sorry, insertion P next is already null. So Q dot F, that next will be P. Happy or not? Q dot F next will be P. So that this new node pointed to by P is taken into account, inserted in that, and that is already null. And then what should I return? Of course, if I say q dot f equal to q dot f next, this will not be visible outside. Right. So I may do this thing. Sorry. This is back, right?
Yes, sir.
Insert that back.
Yes, sir.
Yes, I can check QF or QB, whatever. They are simultaneously. Front doesn't change.
But the spelling of return is wrong.
Spelling of return.
I didn't hear you.
So the return spelling is wrong.
Oops. What is happening? Return this. Let me do one thing. Let me have a print function, which is essentially the traverse function. Node star P. Front. Back there will I do insertion front, yeah, while P. P data, right? This is nothing but the traverse function. Okay, maybe I will randomly add things. Hopefully everything is right. So it will run. Let us see. So this looks fine, right? So maybe I just write what I'm, okay. Then I have to do this, x equal to rand percent 100. Then I say insert, sorry, print insert percent to be, what is that? X. And then I will write X here. Okay, so rand percent 100, right? So maybe I will write percent 2D. Let's see. 83, then 86, 77. So yeah, 15, 93. Okay. So all the time I will have the same random things. So that's not a good thing. So I will use that as right. Okay, happy? So now I will just write the delete function. Okay, it's past 4, but please give me just 10 minutes. So you have started, I will just complete it. Q, DQ, Q, Q. No, I do not. Maybe if I want to free it, then I need it. Anyway, let us have it. If Q is null, of course I cannot DQ. Maybe I should pass an error message. In any case, I cannot DQ from an empty queue. What is important, if Q front and Q back are the same pointers, this means that I have only one element list. So I have to free that thing. And return same thing. Null null typecasted as Q. Otherwise, I will store P equal to Q dot front for freeing later. Free. Oh, no, not F. Next. Then you free. Sorry. Okay, fine. I am freeing Q.F because P I have stored there, and then I will return P Q dot back. Happy?
Yes, sir.
Okay. Then I
Yes,
will
sir.
do one by one 10 dequeuing. 1, 2, 3, 4, 5 lines. Just copy. Only thing is that there is no X here, just I will say dequeue Q. Let us see what happens. Oops. Q cannot be null. Oh. So instead of insert, I write NQ, because that is the correct thing. And here maybe I write this is fine, right? 61, 91, 6, 85, the Q grows like this. And then 61 is served first, so 91, 6, 85, then 91 is served, then 6 is served, 85, 43, 15, 9, 21, 32, 93, and finally an empty Q. Happy?
Yes, sir.
Okay.
But sir, I had to ask one thing about that returning. That since we mentioned that the return type is of Q, so like why did we have to typecast it again with Q type while returning in each case? I didn't understand that thing.
This is actually, I would say, a peculiarity of C. It's not exactly your understanding. I don't know why it does like this, but first of all, note that this notation this bracket notation, curly bracket notation is ambiguous, right? This may mean an array or whatever. Okay. For some reason not clear to me, C does not automatically typecast it to this data type. It does not do it. Even when it knows that in this context, this should be something like Q. The compiler does not do that. And of course, I use this kind of construct pretty frequently. Maybe we need to check whether this is also allowed in MCC. Okay, if this is not allowed, then you have to define something like Q, a new Q or something like that, and set it front and back to these pointers, and then return that new Q or something like that. Okay.
Yes.
Okay. Maybe other compilers refuse to compile this code. I don't know. I only tried it. GCC, it works. Okay. Incidentally, I just forgot to mention one thing. This is just a word. A stack is called a LIFO list, whereas the queue is called a FIFO list. Because this L stands for last, this F, or this F, they stand for first, and this I is in, O is out. Stack last in, first out. Okay. The element that is last inserted, that is taken out first. And here in a queue, whatever is first inserted, it will be taken out first. So this is also sometimes called first come, first serve, a queue. Okay. And we do not have anything like that, last come, first serve or something like that. But anyway, LIFO is a more conventional thing. Okay, so maybe it's already good enough. So I stop here. Shall I upload this code to the web page?
Yes, sir.
Yes.
Please, sir.
Yes, sir.
Do it, but will it give a confusion to students who didn't attend today's class to the effect that Q is part of the syllabus? That this may create confusion, right? For you, I hope there is no confusion. I have done this only to give you some kind of practice with linked list programming. Okay. Okay, I will post it.
Excuse me, sir.
Yeah.
Sir, yesterday near the end of the class, you were discussing an efficient method of doing the quicksort algorithm without the use of an external array. But you said that you would continue it today, but that part you didn't explain today.
I more or less, I didn't write the code, but I explained the algorithm, right?
Yes, sir, that partition function.
Yeah, but I explained the algorithm. You start
Because I was thinking.
Maybe you
Yes.
take this as the pivot. This is your pivot from 1 to n minus 1. You skip less than equal to p, 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 or less than p. If this is less than equal to p here, it is greater than p here. If it is less than here, it is greater than equal to here. And up to this point, you have skipped. So this is say less than equal to p, and up to this point you have skipped because this is this. Now I have here something greater than P here, something less than equal to P here. That is the reason this loop stopped. And that is the reason this loop stopped, right? Now, of course, they may also stop this I and J make a crossover. Okay, so this is I, this is J. If they may make a crossover and J comes to this less than equal to part, I goes to this greater than part, then of course there is nothing else to be done. Otherwise, here what I do, if the loop stops here, I just set T equal to AI, equal to AJ, AJ equal to T. Okay, so that means this less than equal to thing will come here, greater than thing will go here. So this block will grow, this block will grow, and once again I can start the forward march of A, I, and J. Forward march of I and backward march of J. Until either they cross over or once again this situation happens. Once again I will make a swap. I will keep on doing this. Okay, so in fact a code for this. Okay, so eventually what happens? Eventually I have a situation like this. I know this is the entire less than equal to P part, greater than P part. And for example, if this is non-empty, I can simply swap this last element with this. Okay, then what happens? My pivot comes here. All the less than equal to P part goes here, greater than P stays as usual. And then I make quick sort, recursive calls on this part and this part. Okay, so you can look at the slides.
Yes, sir. Understood, sir, the mechanism.
Huh?
Yes, sir, understood the mechanism of the movement of people.
This is a fairly straightforward code, right?
Seems so.
You given in the slides. Maybe
Yes, sir.
But you will get it. Okay. Yeah. So let me know if you have any questions.
Hello, sir.
Tell.
So yesterday you had discussed another question towards the end regarding a string pointer, the constant string pointer.
Yes, yes.
So can you elaborate it, please? Like a similar question had come in the short test also. So how do we modify it? If we are printing S1 again, then
the point is that point is this, right? So we have done something like this, int star s equal to 1, 2, 3. Now this is a constant string. Okay. So if the compiler makes it, I would say, a point that you cannot change this string, then you will encounter an S segmentation fault. So the better way of doing is to do this. Okay, sorry, this is not integer, character. Do this, then there will be no problem.
Sir, but in the question which was given, the S initially stored 463 space 872, and then we had to print 463 using S only.
Yeah, so here if I only want to print 1, I can just put the null pointer, null character here in the place of 2.
Yes, sir, but that was giving a compilation errors.
No, yes, compilation, I didn't see compilation error. Compilation was perfect, runtime error.
No,
yes, sir, sorry.
Segmentation fault is
because this is apparently read-only memory, read-only string. This is also read-only, but only thing this character, this array S is not read-only. So S0, S1, and S2 you cannot access. Okay. So I would suggest that doing this is not a good practice. You may face trouble. This is safe. Okay.
Yes, sir.
Okay. Any other question?
So in NSEM, how many questions will be there, sir?
This format will be very similar to MITSAM. Almost identical. Okay.
Okay, sir.
Okay.
Sir, so this time also there will be a small 2-3 marks question above and 8-9 marks down below.
Yeah, usually it gives this as a small part so that everybody can score.
Yes.
Right. We are teaching everybody, right? Not only the good students. So everybody should be given some mechanism to score.
So what is the weightage of mid-cell and what will be the weightage of end-cell?
We have not decided these things yet. Okay. So, any other questions? Technical, non-technical? Okay, if not, anyway, we will not meet again in this form or in this forum. But anyway, we will be in touch with you over emails. So if you face any difficulty, let us know by emails. And please keep your grudges about short test 2 resolved by talking with the TS. Okay, there may be a couple of issues that I have somehow learned. So we have given them a key, solution key, but of course we could not give any, I would say, every possible solution of problems. So in some situations they may make small errors. So let them know and they will perhaps rectify, provided that they have made an error. Okay. Yeah. So let me conclude. So best wishes for your NSEM and for everything else in the rest of your life. I hope you enjoyed this course, and I tried to be, I would say, I tried to give as much as I can in this very difficult mode. But at least I adopted this online mode a little better than classroom teaching in some sense. For example, I do not have access to a desktop for writing codes, writing Blackboard writing, showing. Anyway, in that sense, this online thing may be a little better. But anyway, just teaching the computer is not really how a teacher likes. Okay. I would love if we could, I could see you in person. But anyway, this is not going to happen in very near future. Okay. Anyway, I still hope that you enjoyed this course, and thanks for being part of it. Take care. Stay safe, and best wishes for the rest of your life. Okay.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you,
Thank you very much, sir.
Thank you, sir.
So thank you, sir.
Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.